brought you HVDC Systems, representing T&D Europe. We'll talk about state of the art. And after Jochen Cornelis Plett from the Horizon promotion project, which was a really high profile project that concluded a few months ago, huge project of huge importance. So we're delighted to have Cornelis here with us today. Finally, we'll have Dirk van Herten, professor from the University of Leuven, who, so forgive me, I forgot Wolfgang Reiser from VESC, and the president of ForSupra. We'll talk about superconductors and what they can do in the future. And as we start looking towards the future, Dirk van Herten will take us through state of the art, building on what's possible and what DC grids could do for us in the future. After all of that, we'll have a Q&A panel. And next slide, please. So a little bit about Current. First of all, this is the second of our series webinar, and Current is an organization that represents innovation network innovation companies in Europe, the voice of European innovation network companies. And really, we're focused on optimizing grids, bringing new technology to grids, and not just optimizing existing grids and getting the most of them, but new grids and developing grids for tomorrow. That's the business we're in, and we're very focused on the Green Deal. And we believe that the network, the power network, is absolutely central to achieving the Green Deal in Europe. So we're very committed to that. Next slide, please. So this is the previous webinar hosted on optimizing power grids for a clean and greener future. That was hosted by Smart Wires in October. Next slide, please. So a little bit about me. I'm vice chair of Current and chief executive of Supernode. And Supernode is a company that develops the housing for superconductors to help with the thermal management. And that's really about expanding the use case. So superconductors are in use today, but in limited circumstance in major cities. And we're working to improve the thermal management so that they work reliably 24/7, and effectively that the superconductors remain super and cool. And one of the applications we're really focused on is the offshore. So bringing those remote renewables, more of them, more economically to markets. So we're delighted to have achieved a statement of feasibility for an offshore, and we're really focused on extending the range and application of this fantastic product. Next slide, please. So just some housekeeping rules. Firstly, this is being recorded, and all the slides will be made available afterwards. So you needn't worry about getting all the details. It's all going to be available, and we'll put it on the current Europe.eu and the supernode.energy websites. So that will be available. In terms of the etiquette and so on, each of the speakers will have approximately 12 minutes. So thereafterwards, we'll have a Q&A. So it'll be interactive. So there'll be some poll questions, and also there'll be an opportunity through a Q&A you should see at the bottom of your Zoom for you to pose questions. And we hope to get to them. We'll have a panel discussion for about 15 minutes at the end of the session. So without further ado, we'll kick off, and we'll have our first speaker, Jochen Balk, and we're delighted to have Jochen. Have we Jochen?
Hello.
Okay.
I hope you can hear me.
Yes, we can hear you. Good afternoon, and thank you very much for joining this webinar.
Thanks a lot to you. I'm trying to start the video. Voila, it seems to work. So thanks a lot for having me. It's a pleasure to address your conference today and say a few words by way of introduction on the offshore strategy, which I assume most of you will will know at this stage. But I'll take the opportunity to walk you, but I'll try to be really quick through a couple of the main points we have raised to set the scene. And I would just like to apologize in advance that I won't be able to stay for the panel discussion in the very end. But I look forward to hearing the outcomes of the conference. So I think we can move directly to the next slide. First of all, why did we decide to do a specific offshore strategy? Because surely offshore renewables is only one part of our effort to reach net zero in mid-century. Clearly because we identified the strategy on the side of offshore renewables as being a particularly steep one, if you like, simply, first of all, because of the steepness of the increase that will be needed looking at offshore renewable energy, because what we have today in the waters with 12 gigawatt mainly in the North Sea is, of course, rather limited compared to the contribution that we consider and our models result in as necessary for offshore renewables to grow in 2030, excuse me, and in 2050, which as you all know by now, goes up to 300 giga for wind and the potential additional 40 gigawatt for ocean energy technologies. So clearly the scale of the upgrade is tremendous and specific to the offshore challenge. Another element which is specific to the offshore challenge is the fact that we are talking about inherently, in a sense, multinational and multi-jurisdictional environment. We're talking about sea basins which are shared by member states. And this, I think, for us is the sort of the bottom line of the whole strategy and the running theme. Exploring this potential in these multinational sea basins does require, in our view, a different degree of cooperation on a number of fronts from what we've seen so far. And the first of them, which you can see already here, is clearly the question how we plan the space and how member states plan the space which is available in those sea basins because it's limited. If we go to the next slide, just to very quickly recap that in our strategy, we put a lot of emphasis on the need to broaden the portfolio of technologies which are available at full commercial scale, which is at the moment offshore wind, and I should say bottom fixed offshore wind. But there are a number of technologies, floating wind, but also tidal, which are, we think, relatively close to availability at full commercial scale, and we'd like to push them in that direction. And there are a number of other technologies a bit further down the road, but also very promising in terms of their potential to deliver and contribute to the overall effort of 2050. As ever in those cases, technology mix, having a broader mix of technologies, is also a question of facilitating system integration, because they can be complementary to a certain extent. If we go to the next slide, just briefly, this is really just to show why this broad portfolio of technologies is so important, because we are speaking, if we look at the North Sea, which is really where efforts so far have concentrated, we're speaking about an environment which is relatively specific, and I would say even unique in an EU offshore context, because it is so shallow. That is to a certain extent still the case in the Baltic Sea, but much less so in the other sea basins that we have, the Atlantic, the Mediterranean, and the Black Sea. And all of those have a potential, but they require different technologies, and we want to tap into all of those. It is also important to stress that tapping this potential fully has a huge huge promise, I would say, in terms of the domestic jobs that it can create in Europe. And those benefits can be fairly far spread, as the picture on the right side here shows. And this is only components for wind energy manufacturing. You could do similar maps for components for either ocean energy technologies or, as it were, grid technologies. They are really technologies which have the potential to benefit many member states and regions in Europe, even those which don't themselves have a coastline. If we come to the next slide, against that background, and again, this enormous upscale, which we consider necessary, what are the key objectives of the strategy? I would name 4 perhaps. First of all, the targets in themselves are important because they set a clear direction, and they are important as a sort of orientation mark for the industry in terms of what is expected of industry, in terms of the capacities which will be needed. Secondly, then based on that, to encourage public and private investment in new infrastructure and also research, both of which very important in the context of this seminar. Clearly, as I said earlier on, the need for regions to work together more efficiently and more closely, and we want to set the frame for that and perhaps offer the right forums to do that. And lastly, for that investment to come forward, what is needed clearly is a clear and stable legal framework which gives investors the kind of certainty and perspective that they need. Coming then to the next slide, which is a little bit crowded, and I won't go, you'll be glad to hear through all of those bubbles. It's just to show that the strategy really aims at looking at those pieces of the puzzle in a comprehensive manner, which do need to fit together to allow that growth to happen. There is, as I said earlier on, the need for maritime spatial planning. So they need to plan the use of the sea space in a rational manner, because it is going to be pretty crowded in some of those areas. Then, and here I'd like to say a few more words on the need for a more integrated grid planning, as well as a clear forward-looking market framework, which will allow this growth to happen. This, I think, is then touches or comes close to what is at the heart of the discussion today. What is the kind of offshore infrastructure that we need, and what is the, let's say, the kind of topology that we need for that? We clearly do think that these offshore grid systems need to become more integrated. We sometimes do use the word meshed, which is in a sense an advanced stage of the process. In the shorter term, excuse me, we think what is needed is to facilitate, let's say, the deployment of more integrated structure, such as hybrid assets in particular, which combine grid solutions with the interconnector solutions with the connection of the offshore wind farms. We do think this is a necessary part of an overall efficient grid design, and that requires a certain number of things. That requires indeed a more integrated approach to grid planning. That does require clarity on market rules, and it does require also clarity on the sharing of costs and benefits in the context of such an integrated grid. So these are some of the key elements we highlight. There is then also an important dimension in terms of industrial upscale, but also research and innovation. And I would just like to briefly touch on the latter, because clearly there is some efforts still to do in terms of our RI policy, if we want to make those integrated grid solutions available, again, at full scale in the water. This is why we have spoken relatively clearly about what we intend to do in the context of Horizon Europe, where we think that such large-scale demonstration projects for HVDC are necessary and should indeed be part of the next work program, to allow basically to move also on that front from ultimately then from demonstration to availability and rollout on full commercial scale. These are some of the key issues. I could mention a couple of others, but I think in the interest of time, I'll leave it at that and move to the last slide in this presentation, which is really about the next steps that we have in mind. Still this year, we hope to come out with a proposal for the 10E revision. That is clearly a key piece of legislation when we look at offshore grid planning, and we will certainly address this element. in the context of our proposal for a revised 10-year regulation, still in December. Then in March next year, there is an important deadline in terms of the national maritime spatial plans, which need to be presented to the Commission in March, and we want to make sure that those are, let's say, both compatible with each other, but also that they're compatible with our energy sector planning, as expressed in the NECPs. That is an important element. And there'll be a larger legislative package then towards the middle of next year, including the Renewable Energy Directive, which is certainly going to be important in that context. I do want to mention in closing that apart from those sort of more formal initiatives, we do want to follow up on the strategy by, let's say, reinvigorating and also specifying the activities in the context of the Clean Energy Industrial Forum, because we do think that closer cooperation between industry and the public sector is an important precondition for making this offshore vision come true. And we do also intend in the course of next year to intensify the cooperation in the context of the regional high-level groups, which have all started to look into the offshore subject. And we're also looking at at some kind of conference event in the middle of next year. So a number of follow-up actions planned. That's all I would say by way of introduction. Thanks very much for your attention, and I'm looking very much forward to the rest of this discussion.
Thank you very much, Joachim. And I have one question, because I know you won't be joining us for the Q&A. I can cut to the message, because I've seen the message in a number of these, and the technology is not really a showstopper. The big challenges you have in relation to aligning the regulations with the transition to 2050, and the regulations were designed. So that's a big job you have with your colleagues in the Commission. So we wish you very well, and thank you for taking the time. I don't know if you have any sense of the technology, but are you confident that the technology is available?
Well, indeed, as you say, I think what we hear from industry is exactly that message. Technology can be delivered, and I think we are confident that is in fact the case. But it has to be also basically delivered at the right time and at the right scale. And I mean, that's why we do think there is still a certain role also for the public sector in basically bridging that gap to making the technology available. Again, I think it's more a question, technologically everything is basically already feasible. I think all solutions are in principle out there, but I think we have to prove them in real life. I think that's the thing. We have to prove them in the real existing energy system. And that is then exactly, as you said, basically touches on the interaction between the technology and the regulatory framework, which will allow its deployment. I think that's the real challenge.
Thank you very much. Thank you for that. Our next speaker is Arnoldus van Vingard from the Fraunhofer Institute for Wind Energy Systems, the Chief Scientist. Over to you, Arno.
Yep. Hello, and welcome from me as well. Happy to be here. And I wanted to give a small presentation on energy in 2050, seen from the 2050 point of view. Next. Okay, since I'm from wind energy, I'll talk a little bit. Since I've been in wind energy turbines have been growing from 55 kilowatts with about 10-meter long blades up to the 12 megawatt Haliade, which has blades which are over 100 meters high. And as you can see, to the buildings in the background is starting to give some competition to the Eiffel Tower already. So we're getting a North Sea full of Eiffel Towers. Next. And not just the size of the individual turbines have been growing, wind energy as a whole has been growing quite nicely as well, up to about 500 gigawatts. In the insert, you can see the offshore energy, which is following a similar trajectory. It's just that it's like maybe some 20 years behind. Next. So this is all very good, and this is typically the point where I congratulate the industry on a job well done. And then, okay, where do we need to go? Next, let me zoom in here. So next. So we've done 500 gigawatts, but we need to do about 18 terawatts. And that's a different number than Joachim mentioned, the previous speaker, because I'm looking actually at the energy needed in the whole world. Next. And it's a fairly simple calculation, actually. The global current energy use, we're not talking electricity, we're talking energy here, is 18 terawatts. Yep, the population will slightly increase, but the energy efficiency too. So let's stick to the 18 terawatts here for a moment. And if wind energy is to do 1/3 of that, and you calculate a 1/3 capacity factor, you need about 18 terawatts of wind installed by 2050, which is a very different number than Joachim mentioned. And it's worldwide, and it's also more on the need for a totally carbon-free system. So we'll need something similar for solar energy, and we'll need an electricity grid to transfer all of this current electricity use that we've been doing so far, plus transport, plus heating for the whole world, which is about 18 terawatts plus spare capacity because of these renewable energies not always having the constant supply that you are used to from conventional electricity users. So a normal strategy would be like, okay, we need to add a transmission line here and a transmission line there, and we need to grow the national grids together into a more European grid and connect the European grid to the rest of the world. That is the conventional way of setting up a strategy. Next. Now, in contrast to John and Joachim, I don't think the regulatory framework is the major stumbling block. I think the major stumbling block is simply politics. So meet Markus Söder, is the Prime Minister of Bavaria, of the state of Bavaria in the south of Germany. And it's also Bavaria that is the B in BMW. So it's a very car-centric country. Next. So it's really it's really quite exciting that he's actually suggesting to stop selling cars on fossil fuels from 2035, so 15 years from now. And he's very consistent in that. Next. Because he said the same thing in 2007, except then his cutoff date was 2020, which obviously we didn't make. And I'm really curious to hear his opinion on the matter in 2035. Next. Yeah, okay, that's a little bit harsh judgment, but maybe not totally undeserved. The reality is more that politicians inherently seem to have a lot of trouble thinking more than 2 elections ahead. Next. So if you go to Germany again, this is the map of Germany you see here. Basically, Germany has wind energy, loads of it in the north, and loads of solar power in the south. So it would be quite nice to connect the two, to shovel electricity around depending on the amount of sun and wind we actually have. And there you can see here in the comment from Terence how much trouble it has been to actually get everybody to agree on this very one transmission line. And that's, in my opinion, something that will come back to bite us for this kind of stuff. Next. But let's look at it at a different point of view. Let's say we are in 2050 now, hooray, and we've got 100% carbon-free energy supply for the whole world. So what exactly does a grid that can handle this 18 terawatt electricity couples major population center across the world with the variable influx from solar and wind and other renewable energies? So which technologies, standards, regulations do we actually use? And how did we get there? What is necessary and what in which order? And that's a different strategy from taking the current grids and adding a line here and adding a line there. This is more like, okay, what do we need in 2050? Next. And then let me show you a kind of reversed Gantt chart. And this is also useful for slapping politicians around the ears with the actual need for not just talking about it, but actually doing something. So we need to be ready by 2050. Everybody agreed on that part, which means, you know, you will be digging in the 10 years before that, and hopefully starting a little bit earlier than that, which means that you got a legal framework in place before that. You need to get the planning in place for that. And you need to work really hard on the research if you want to talk about types of grid just about right now. One thing on the cost development that we also may be neglected: materials may run out or become more expensive if we are simply starting to dig out the whole world for, well, for instance, making this 10,000 Eiffel Towers in the North Sea. But on the other hand, we can now go chuck, 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 like T-Ford style, have automated production technology for those wind turbines. And that would probably also help. And I see similar advantages of scale in other fields, but it's a very, very major task. Next slide. And talking about national grids, I mean, this is from The Guardian, you know, a plan to couple the largest solar park in the world to be built in Australia with Singapore. And I mean, that looks like quite a distance. Next. Putting actually the map of Europe in more or less the same scale on top of that will show you how big that really is. And it's also showing how possible and necessary it will be to couple everybody on the planet together in order to get this thing actually working. And why are we doing this? Next slide. Okay, so in the last, I mean, we've had a temperature increase of 1 degree. And I mean, 1 degree, come on, it's hardly noticeable. You've got more on a day-to-day variation. So what happened in the last 2000 years? So this goes from brutally executing somebody for saying that people should be a bit nicer to each other, all the way to the pinnacle of modern civilization. And let's see what the temperature did in that time. Next. And here we go. So there is the medieval warm period. There's the little ice age around the 1700s. And depending on how you choose your reference point, you can pretty much fit in the whole temperature change over that time in a bandwidth from more or less minus half a degree to plus half a degree centigrade. So it's really been quite mild, except of course for the last part, which is why I think the coming period can be called interesting times. And just how interesting they're going to be is very much dependent on all of us actually getting together and doing something about this. So that's more or less what I wanted to say here. Next slide. Thank you for your attention. Next slide. We get money from all kinds of nice people, and I'm really grateful for that. Thank you.
Thank you very much, Arno. I have to say I really enjoyed the reverse Gantt chart and looking at it back from 2050. What do we need to do today? And it's obvious we can't. Business as usual will fail us miserably. So we need to innovate, and we need to be creative and brave. So we've got 100 years out of the carbon, and now we need to learn to live without it. So to my next speaker, who will start that conversation. Next up, we have Jochen Kreisel from the people who brought us the HVDC that has brought us together to this point. Over to you, Jochen.
Well, thank you very much. Good afternoon to everybody out there. So my role in this webinar is to talk a little bit about why DC grids, and maybe we can go to the next slide already in order to deal with the limited time frame. So before talking about DC a little bit, very little about T&D Europe, which may not been that well known as some of the companies being member of it. So T&D Europe is the association of suppliers, technology providers for electrical networks in Europe, and you see a lot of pretty well-known industrial players on this slide, and a lot of national trade associations who are the main members and who may not be that well known. And we are representing a pretty relevant industry in Europe, and what I would like to make you aware is also that Europe has always been, you may say, it's fair to say, leading in developing technologies for transmission and distribution networks. And if you look at the players, then you will see that all their research facilities, production facilities are still pretty much Europe-centric. And I think that has to do with a successful history of in the industrial cluster of one of the most challenging over a long period of time, I would say the most challenging power systems in the world, integrated more than any other, multinational than any other power system in the world, resulting in technological challenges, which together with the network operators, our industry was usually able to solve. And we had the opportunity to grow on that. And we strongly believe that the transition we are talking about now, among many other things that we have to do, is also an opportunity to continue this historic success story. So enough about the industry. Now let's talk about DC. Next slide, please. And I start with a slide on AC, because we should not forget we are enjoying more than 100 years of supply with electricity. As I said before, we have one of the most powerful, sophisticated power systems in Europe, and with an extremely high reliability of supply, quality of supply, and all that was done without DC. So why did we choose alternating current AC? Well, there are a number of advantages which were particularly relevant in the early days with the technologies at that time. So you can transform voltages easily with AC, and that means you can go to higher voltages for energy efficient and cost efficient transmission, and at the same time you can go to low voltage levels for safety reasons wherever you use the energy. It is possible to interrupt even very high currents in AC, which is very important in order to ensure safety in the system. It's also very easy to convert mechanical energy into electricity and vice versa, which are the main applications. Most electricity is somehow generated from mechanical energy, and in the end, motors are also a big area of application. There are some other advantages. I don't want to go too much into details here for the sake of time, and this is a DC speech, but a few words on the limitations. So the longer transmission became, the more difficult it was and is. And it was also very difficult to combine cables with very high voltages. So which means it excluded more or less cables from transmission tasks, because for transmission you need high voltages, but usually you want to transmit over a reasonably long distance, at least some 100 kilometers, and that was more or less impossible. So next slide. The conclusion is, for the traditional tasks, particularly looking at the European system, which by purpose is shown on the left side, we have a system with built out of national systems, which were early connected to help out each other, to share reserves, to mutually cooperate, but they were still balanced, at least most of them were balanced on a national, sometimes even sub-national level. And for that, an AC interconnected power system is a very good fit, to say the perfect solution. But now next slide. That's not describing the future we are heading for. So with renewables, we will see, and have seen that already, geographical concentrations of generation. We will see a need for longer distances in transmission, and I would like to add even the highly distributed resources, such as, if I go to the extreme, rooftop solar, will generate local peaks, which will need to be distributed over longer distances in order to benefit from complementary weather situations and to provide some flexibility or balancing for load and generation. And there's another driver. If we talk about offshore, then we need to talk about cables. And here, remember, longer cables were not very compatible with high transmission capacities. And then some more reasons. We will see in this European power system, which is indicated, the future power system, which is indicated on the left side with longer transmission needs and distances, we will also see much more variations of the load flow situations. Traditionally, variation of load flow were primarily defined by the distribution of load, of demand. And that was quite homogeneous, and particularly it was quite stable. So if you knew 1 year, you basically knew every year. And you could adjust the supply system accordingly. But with renewables, we will see stronger variations, because depending on the weather situation, we will see strong feeding clusters in one part of the system, and on the other, next month maybe, or maybe even next day, on a totally different place of the system, depending on the geographical distribution of weather. And that means the system needs to be able to cope with much more different load flow situations all over the globe, the continent. And here, an active network control would definitely be beneficial. I don't want to go too much into details, but AC systems are passively controlled, whereas DC systems have to be actively controlled, which is an additional challenge, but it also offers additional opportunities, which fit pretty well to this future world we are talking about. So that's the reason why we are talking about DC, and our industry, which has developed HVDC since the 50s for special applications, has seen that quite early and invested a lot in making this technology ready in time. And here I would like to go back to the reversed Gantt chart. I think we are pretty well aware of this challenge. Next slide. So a lot has been done technology-wise. We have developed a new generation of HVDC, which is more compatible with the tasks of building hybrid systems, both AC and DC, and well, smoothly cooperating the two parts of the system, the so-called voltage source converter technology, which started pretty small in the late 90s, and in the meantime has reached the gigawatt range, and by that can be called a real transmission technology. At the same time, our industry also developed cables further, the environmentally friendly XLPE cables, so plastic cables, you may say, simplified, are also a relatively young technology, starting in the 90s, and today we have increased operating voltages to 525,000 volts, 525 kilovolts, which allows us to build transmission corridors in the gigawatt range again. So that's what we usually call a transmission line. So a lot has happened. Something has to happen on top of that. And here it's important to talk a little bit about how we dealt with HVDC traditionally. It's a proven technology, and how we will have to use it in future. Traditionally, HVDC was used for point-to-point projects. So if you wanted to connect, for instance, a remote hydropower plant to centers of load, it's one of the classical applications. Then you build one line from the power plant to the center of load, and this was a point-to-point, one line delivered usually by one supplier as one project. The same applies to multiple subsea interconnectors, which we have all around Scandinavia. By the way, this is one of the reasons why this technology was developed strongly there. The combination of subsea cables and HVDC, all point-to-point. But in future, we are talking about developing a sort of an overlay network, a meshed infrastructure. And that means this will be built much more like a network, where you don't build individual lines, you build nodes and connect them with lines, and all this coming from different vendors. So all the components have to become much more interoperable, and a certain level of standardization will also be needed in order to allow us to build a grid step by step, because obviously nobody will order a grid in one big project. So that is what we have to learn and to develop in time. Next slide. Also recently, a lot of achievements have been done. I'm just quoting two of them, which we, our industry and network operators together, were able to run with the support of the European Commission. One project from the 7th Framework Program, the other one funded from Horizon 2020. Best, fast, and promotion. We will hear about promotion later, so I don't need to talk too much about them. What I would like to say is they created a lot of groundwork for this interoperability, for components, for grids. So I think we did very important steps. But the next step is that we now need to build real life, real experience. And I'm very glad to hear that Joachim Balker mentioned that already. So as an, and then maybe you can click once more, because there is a small animation that should show up then. So somehow we need to go live now. We need to build real life experience, to sort out the nitty-gritty details that usually only appear once you go in the harsh operational environment. There is a risk to be managed. So this is something where concerted societal effort is certainly needed, and I think that applies for the whole energy transition. We would call that, it's a little bit Europe's man to the moon project, the energy transition, and being prepared for an HVDC overlay grid infrastructure, not only offshore, but also spanning to the continent. This has to be developed with a holistic view, of course, is certainly one of the bigger challenges we have to face in there. However, I would like to support also what Joachim Balker has said. He's not concerned about technology. If we look what we have achieved in the energy transition so far over the past 20 years, and we are in a situation that I would say the early promoters of renewables, even the early promoters, not the skeptics, the promoters, would never have expected in such time. And technology was not at all the showstopper. And we are very confident that it will also not be the showstopper in future, but we have to plan and execute it, of course, considering the long development times infrastructure usually has and requires. So that was a quick run. I hope it wasn't too quick, but I had to cope with my time slot. Thank you very much.
Thank you, Joachim. Thank you for that. And I think what's interesting there is the call to arms and talk about a moonshot. So we have reverse Gantt charts and now a moonshot. And I also want to acknowledge the great work, Joachim, and the inspiration that we took in our company from Best Paths, because they demonstrated they did a type test for a superconducting cable that could move beyond 3 gigawatts and more to come. So there's hope. Speaking of which, we're on to our next speaker, and we will have some questions coming up. We have a poll which we'll run, so we'll be asking a question or two, and we'd encourage you to submit questions through the Q&A function as well. So our next speaker is Cornelis Platt, who is responsible and involved for many years with the promotion project. I can't vote, so I hope you do. Over to you, Cornelis, and welcome. Thank you.
Thank you, John. Also, thank you for the invitation to speak here. So from the previous presentations, the need for DC grids, I think, is quite clear. And what also is shown by the previous presentations is that the scale that justifies HVDC really also requires international collaboration. So unless we want to get lost in the Babylonian confusion, in my presentation really like to work on some common language and to address the aspects of hybrid and meshed HVDC grids, what they mean, what the development status is, and to discuss two major challenges. So let's first go to the concept of hybrid. Can you go to the next slide, please? You probably know the word hybrid best from hybrid car, but it has many different meanings. And in general, you could say a hybrid thing is something that is a combination of two different things. So it has qualities relating to both of those things. So the idea is really to get the best of both worlds and the worst of neither. And you could really see it as an attempt to elude the famous engineering law of the conservation of misery. And applied to HVDC, it has several different meanings, which have already come by today. So the first is a hybrid transmission system. Jochen already mentioned it. It's a transmission system consisting of both AC and DC connections within the same interconnected electrical grid. And quite often the DC links in such a grid are also called embedded HVDC links. And the way that they come about is that they typically are regular AC grid expansions or reinforcements, but that in those projects, due to environmental or societal reasons, cables had to be used rather than transmission lines. And if those projects are longer than a certain distance, the AC technology is no longer viable and DC must be used. Now, this also brings another advantage with it, which is that if you use VSC HVDC technology, the link is fully controllable and it can actually optimize the AC grid operation in terms of congestion, losses, reactive power management, and it adds to a grid reinforcement without increasing the local fault levels. Those kind of systems are already in operation today. So examples are, for example, the Cobra link between the Netherlands and Denmark, the Western link in the UK, or the Caithness-Moray interconnection in Scotland. And onshore, we have, of course, the Enelfa project between Spain and France, and the Allegro project, which was recently commissioned between Belgium and Germany. And many more of these types of projects are in the pipeline. For example, the German HVDC corridors. Next up is a hybrid HVDC system. So this is an HVDC system in which actually different converter technologies are mixed. For example, the classic line commutated converters and the more modern VSC converters. This really tries to exploit the aspects for LCC converters of low cost, high capacity, and its fault blocking capacity, and combine this with the benefits of VSC, which is, of course, its low footprint and its low AC grid impact, the high level of controllability it has. Of course, combining different technologies can also have some drawbacks, such as the fault behavior, which is very different for LCC or VSC converters, and the power flow direction. Some specific examples or some specific cases, actually, this is not a problem. So, for example, in a case where power flow is going predominantly in one direction, you could apply this type of hybrid HVDC system. One example is the Wudong-de project in China, which is currently in commissioning. This is actually a 3-terminal project, of which one terminal is 8 gigawatts. And this type of rating is not yet available in VSC. So this has to be LCC. And the other terminals are both 5 and 3 gigawatts at 800 kV. Yeah, time will tell how successful this system is. And then the third hybrid system is a hybrid interconnector. And this is what Mr. Balker referred to earlier in his presentation, which combines two different transmission purposes in the same asset, the same infrastructure. So for the most well-known case is to combine interconnection between two countries with offshore wind export, as you can see in the picture on the slide. Now, the main advantage of this is that you can better utilize the infrastructure. So when there's no wind blowing, you can use the offshore export link infrastructure for interconnection. And this gives you a better return on investment. And of course, in the end, a lower price for the consumers. Technically, this is of course possible, but up to today, many regulatory challenges stop this from happening. For example, different regulatory regimes for interconnectors and offshore wind export assets. The 70% rule, that 70% of the capacity of the interconnector must be made available to the market, is one example of this. Questions about which bidding zone the wind farm should be in, how to handle subsidies to the offshore wind, if the subsidies from one country to wind must be applied to energy that is then flowing to another country, and questions about who owns different parts of the link. Typically also different projects, different types of links are different projects and have different organizations. That can lead to differences in project timing, which might then lead to the requirement for anticipatory investment and regulatory issues there, and different procurement models and procurement streams, which could lead to the need for multi-vendor interoperability, which is still a bit of a challenge. That doesn't mean that those systems aren't actually in operation. One example is, for example, Kriegers Flak, which, even though this is not purely HVDC, is a hybrid asset. And two more projects, the Wind Connector and the Nautilus Link, are actually in development at the moment and really making steps towards making this a reality. We really think that there are many more of these types of projects to come. They are the most efficient way of using offshore HVDC grid infrastructure, and can thus be seen as a building block for meshed offshore HVDC grids. Next slide, please. Then there are also two types of hybrid components in HVDC grids. So one famous one is, of course, the hybrid HVDC circuit breaker, which combines the low cost, low loss, and the high dielectric withstand properties of mechanical switches with the high speed of operation and controllability of power electronic equipment. And the technology for such equipment works. We tested a 350,000 volt version in the promotion project, and several similar types are in operation in China today. The challenge in getting those things to work is, though, the system integration. So how do you integrate a DC circuit breaker in a multi-vendor setting with, at the moment, no guidance from a DC system grid code in place? And the last type of component that I would like to discuss here is a hybrid NMC VSC converter. So this is a multi-level modular converter, which combines both half-bridge modules, which have relatively low cost, could be seen as efficient and reliable, with full-bridge modules, which have a high fault current blocking capability and reduced voltage operation capability, depending on the ratio between half-bridge and full-bridge modules. And as such, they could be an alternative for HVDC circuit breakers in what we call non-selective fault clearing schemes. Many half-bridge, purely half-bridge based converters are already in operation, and the first fully full-bridge converters are in development, Ultranet. The main challenge in making a hybrid half-bridge, full-bridge converter is how you energize and charge the submodules in such a converter. That doesn't mean it's not possible. So I would like to refer to the same project I mentioned before, Wudongde in China, where the VSC link side converter is actually a hybrid NMC VSC converter. And also in Europe, there may be an application in point-to-point bipole offshore wind farm connections in order to handle metallic return faults. Next slide, please. So what are then meshed DC grids, and what can they do for us? Next slide, please. So what you see now is a map of all the currently planned and in operation HVDC links in Europe. What you can see is that these are all predominantly point-to-point, single purpose, and what you can't see from the map, but is the case, is single vendor projects. And yeah, you can see that it's already becoming quite spaghetti. Many links are in place, but it's not yet possible to make a grid out of this, because as indicated by the different colors, these lines don't have different voltages, they have different voltages and also different converter configurations. The first sign of the hybrid transmission systems are really already coming into place. So the blue lines, for example, the Caithness-Murray which is an embedded HVDC link in Scotland. And at the bottom, you can see the tip of the Ultranet link in Germany. But also hybrid interconnectors. So the two red lines, the top one is the wind connector and the bottom one is the Nautilus link, are already on the map. And these hybrid systems, they all happen to be multi-terminal, but not yet meshed. So what is the difference? Can you go to the next slide, please? So on the left, you see point-to-point, an HVDC system made out of two point-to-point systems. This is often also referred to as radial systems, where you have converters on each line end. This is the paradigm for HVDC grid building today. So the reason for this is that you have generally easier project development with only one single vendor delivering both converter stations, one single purpose, and each link can be optimized for its application. Therefore, you could say that this is relatively mature and a widely applied way of building HVDC. A challenge could be, if you have many of those, to integrate many terminals from different vendors that are closely located together in the AC grid. Now, an alternative to this could be the radial multi-terminal system, which you see in the middle. And this could really serve the same transmission need, but what you can immediately see is that we need fewer converters for this. We combine the two links on the left-hand side and have one converter to go out. And this immediately leads, of course, to lower cost, a lower footprint, lower losses, and a higher availability of the system as a whole. And it allows us, as in the example of a hybrid interconnector, to combine the purposes and increase the utilization of the grid. It also comes with challenges, of course. For example, the coordination between the different projects, the different parts of this DC grid and their partners, and multi-vendor interoperability. Several of those types of grids have already been built and put into operation in China, which means that from a technical perspective, in the right setting, which is one country and one TSO, this can work. And in Europe, several examples are in development, like the Caithness-Moray Shetland extension, Ultranet, and Eurasia. The only problem is, though, that in case of a DC fault, there's no redundant path. And that is problematic for large HVDC system ratings when you go into the multi-gigawatt range. Because in that case, we might exceed the maximum loss of infeed in the AC synchronous area that it is connected to. And one solution to this could be the meshed multi-terminal system, which you see on the right. Here, we can reduce the impact of a DC fault on the AC system by rerouting power through a redundant path. This comes, of course, at the cost of having to have a DC grid protection in place, for example, the hybrid breakers or even hybrid converters, and the need for an additional cable and cable capacity. It is technically possible. In China, they are commissioning at the moment such a grid. But the real benefit of such a grid comes in cross-border, large-scale settings in which it combines different purposes. And that's really hard to achieve in international settings. It requires a very strong international collaboration and political commitment, and multi-vendor interoperability, which could, of course, be helped by a DC system grid code. Next slide, please. And two challenges that we have in the EU in realizing this is, on the one hand, the number of cables and converters that we need to build. So it is always a good idea to minimize the amount of cable necessary in a transmission grid in order to minimize the cost and environmental and societal impact. So therefore, it's good to cluster wind farms to hubs and then use the highest possible cable rating to go to shore. In the EU, we have an offshore wind target of 300 gigawatts. And on top of that, you have to add also interconnection targets. And if you then look at the state-of-the-art HVDC cable ratings, which is inching towards 3 gigawatts, you can see that we need hundreds of cable corridors and also hundreds of associated onshore converter stations. Now, in order to minimize the impact on the surrounding countries in the Netherlands, it is really important that we work towards having higher capacity cables and smaller converters. And the question is, of course, what can we do to do so? Could we, for example, go to a lower voltage transmission grid with superconducting cables and converters based on silicon carbide technology? The other big problem, regardless of the technology used, is the impact on the AC grids. So in Central Europe, this loss of in-feed is 3 gigawatts. Elsewhere in Europe, it is actually substantially lower. You can see that the maximum cable size is approaching this loss of in-feed or already exceeding it. And if we want to actually realize these high capacity cables to minimize the impact on the environment and society, we need to find a way to handle this maximum loss of in-feed. And meshed HVDC grids could alleviate this, but of course requires strong international collaboration. Next slide, please. And promotion, we did quite a lot of research into how to solve this. And we came to the conclusion also that the technology for building such meshed HVDC grids is in principle ready, but that we need a significant amount of work on standardization and on international collaboration and coordination in order to make this work. And we are convinced that we need a full-scale pilot project which shows those technologies at full scale and not only demonstrates the technology, but really realizes the benefits that those technologies can unlock. Next slide, please.
Yes.
So just to conclude, there are many words, many uses of the word hybrid, so be careful about this in your conversations. We already have a hybrid AC and DC transmission system. Many hybrid interconnector and offshore wind farm export links are in development at the moment. We see these really as building blocks for offshore DC grids. The technology for those grids is ready, but we require more international coordination, harmonization, and standardization. And we really need more work on increasing the power density of cables and converters. And then lastly, the maximum loss of in-feed today is really the main restriction on cable capacity that we can apply in a grid. And a meshed grid topology could bring some relief here. So thank you for your attention, and I hope you enjoy the rest of the day.
Thanks, Cornelis. You crammed a lot in there. So we have another question going out on the poll. I suppose takeaways from that, we need a bigger boat. We need bigger cables in a meshed environment. There's a lot to do, and it's going to be tricky in a multi-jurisdictional environment to do it rather than in a single large grid. Thank you very much. Our next speaker is Wolfgang, who will talk about superconductors. And is Wolfgang there to join us? Yes, over to you, Wolfgang, and we'll have to hold you to the 12 minutes. Thank you.
Oh yeah. Yep. I think everybody can hear me now.
Yeah. Yes. Welcome.
Okay. Yeah. Thank you for the last question. I think I will give you some hints and answers on the last question about superconductivity. I will not introduce here the Vision electric superconductors and the EV Supra, which is the superconducting association. You will find on the last pages our links and also some contact details. Next page, please. I want to start with some words about the Best Path project, which was already mentioned by Jochen Kreusel. And I just want to highlight two topics out of the Best Path project. It says gigawatt scale superconducting cables are technical, mature, and cost competitive for high power transmission. And cost competitive means here total cost of ownership. And the recommendation for policy is to allow feasibility studies and public tenders and incentives for the deployment of this technology in the grids. And I think that is one of the important messages out of Best Path. I just want to give you a few characteristics of superconductors. Next page, please. Here you see a few pictures. On the right above picture, you see the difference in size between a copper and a superconductor. And just a word on the current capacity. If you want to conduct 1000 current with amps current with copper, you need approximately 1000 square millimeter of cross section. And you can do that just with 2 superconductor tapes, each of that having 1 square millimeter. So the superconductor tape you see here has a size of 10 or 12 millimeter in width and 0.1 millimeter in thickness. So that is the comparable relation, factor 500 on the current carrying capacity between copper and superconductor. And of course, you see directly that there is a big material efficiency, a high material efficiency in superconductor. That means also through the production process, carbon footprint of superconductor is much lower than that of relevant copper or aluminum. In the middle, you see a aluminum bus bar system representing 20 kiloamps. And above that, there is a superconducting bar also representing 20 kiloamps. So you have an idea about the difference in size and how is that possible that such a very small, tiny conductor can carry that high current. What about heating? Copper cables get warm. Why not superconductors? And the reason is, if superconductors are on their operating temperature, and that is one of the things you have to keep in mind, the operating temperature is about minus 200 Celsius or 70 Kelvin, which is liquid nitrogen. If you are on that temperature, there is absolutely zero resistance, which means that the superconductors show the highest energy efficiency. And that is that applies for DC currents. In the bottom picture, you see the electrical losses, and you see that red line, and you see there is absolutely zero electrical losses if the current is in the right range. Of course, there are not only positive things, but also something negative. And the negative is a relatively high capex, a relatively high cost of production still for that superconductor. And on most applications, we get a return on invest between 1 and 12 years, depending on the application, depending on the system we are looking to. Next page, please. I just want to show you a few things, a few parts where superconductors already have demonstrated that they are useful and that they can be used. What you see here is a superconductor wind generator, and that superconductor wind generator was exchanged against a permanent magnet generator, and you see a reduction on the diameter down to 75% and a reduction on the total mass of lower than 65%. And here you see the difference in size. Next page. Then another, please, next page. Next page. Yes, thank you. There are also possibilities of doing a superconducting fault current limiter. That happens if the current is higher than the superconductor can carry. And in this case, the superconductor leaves the superconducting state and becomes normal conducting. And because it has such a small cross-section, it has then a very high resistance, which limits the fault current. And it can be used in AC and also in DC grids, which might be helpful for switching off DC currents. Next page. Another example is the use in a normal 10 kV cable. This cable is running since 2013 in Essen, and the reason for that was in the city center there was a 110 kV transformer station, and during the years the city center has developed into a pedestrian zone, and it looked like that it will be very difficult if once there is a fault occurring. So they wanted to remove the the 110 kV out of the inner city and removed it out to a suburban area and installed a 40 MVA superconducting cable to that city center, and that was a very good solution for that place. This is running since 2013 without any problem. So superconductors, they are there and they can be used. Next page. And we also demonstrated that in an industrial application at BASF here in Ludwigshafen. We have installed a 20 kiloamp DC connection in a chlorine plant, and that installation was done during the operation. The reason for that was we wanted to demonstrate that it is ready for industrial use. We did all the risk assessments. We did during real life production conditions, and all the safety, health, and environmental regulations which BASF has. And I think in the meantime that BASF has the most strict regulations in the world. And we are now working on an upgrade of that. We are going to build a demonstrator of 200 kiloamps in a aluminum plant of TRIMET, and the installation of the demonstrator should be done in 2021. Next page. Another part where we think is very important are data centers. Superconductors there are the missing link. Why? More than 10 years ago, studies had been done by Intel about using DC for data centers. In the meantime, more than 25 data centers worldwide are running on DC, but the situation is that if they are getting larger, the current is larger, and the current losses on copper or aluminum bus bars or cables are eating up the higher efficiency of DC. So the superconducting technology is the missing link to capture the advantage of DC technology in data center environments. And the superconductor technology is not only for data centers, the missing link, but also for others, which I will explain a little bit later. Next page, please. So we made an analysis on ROM-based estimates, and what you see on these graphics is that depending on the power of a data center, the return on invest is better, or other, the net saving is increasing. So you should keep in mind the higher power, the better for superconductors, for DC superconductors it is. So we are coming down even to a payback period of around 1 year for 80 megawatt. Next page. Jump over that. We are coming now to our vision, and we want to marry high currents with medium voltage to reach high power MVDC, and that is the situation where we are looking for. And we are coming here to a possibility of multiple gigawatt. Go to the next page, please. You can read it all after you have downloaded the slides. I have to hurry a little bit up because I got a sign. Go to the next page, and that is the more important one. If you see here the medium voltage source converters, you easily can imagine that with a level of plus minus 40 kV, we can reach easily with 50 kiloamps, 5 gigawatt. And that is the range we are looking for, even going up to 10 gigawatt. And that with the same or lower capex and definitely lower OPEX compared to cable systems. Next page. There was a requirement for larger capacity cables, and here you see an example of that. a cross conductor, which is consisting of a lot of small tapes of superconductors, has been developed by the KIT. The Vision Electric Superconductor has licensed that on commercial production and marketing and sales. And you see the model of a 40 kiloamp cable, which has a diameter of 100 millimeters. And if we cool that down to 20K, which is the liquid hydrogen, then we can go up to 100 kiloamps. Next page, please. Just a comparison on the SuedLink. And that was just a rough estimate on the costs if we were doing the SuedLink with superconductors. First of all, the converter stations will be lower in costs. Superconductors cables will be much higher than normal conductor cables. Cryotechnology is in addition, but we also have here lower costs because of the installation. And that is something which is really helping us in promoting that technology.
So
and at the end,
we need to cut it there, please.
The last page, and that is yes, we have the difficulty to land 35 to 40 gigawatts to Germany, and that is possible with superconducting MVDC. And if we combine that with LH2, there's double usage. Thank you very much.
Okay, so we have, as you can see, our presenters have a lot to say, and we probably could have got a half a day out of this. So thank you very much. Takeaways there are that the technology is closer, and we just need some customers to adopt it. So I think thank you very much for that, Wolfgang. We may come back to this again. So our next speaker is Dirk Van Hertem, professor from Leuven. And over to you, Dirk. And we have another questionnaire as well. So over to you, Dirk.
Yeah, thank you very much for the opportunity to speak. I will be quick. I also have too many slides. My apologies for that. There are also many animations. We'll see how it goes. I'll try to bring my messages over. Next slide, please. So yeah, we have ambitious goals. This has been mentioned before. We would like to have 450 gigawatt of offshore wind by 2050. Some say it's only 300 gigawatts. So 450, 300 doesn't really matter. It's an enormous amount. And if you go to the next slide or the next animation, if we look into that, what Wind Europe says is that we would like to have 200 gigawatt in the North Sea. And just for fun, if we have 200 gigawatt in the North Sea and we have 5 gigawatt links, which is not current day practice, but about to double. Next. Can you push another time? Yeah, this would be more or less the number of lines that you would need to put in the system. Double the capacity, the maximum capacity that you have today. Clearly, this is going to look like spaghetti. This is not really a nice thing to do. So next. What we actually will need is a DC grid, but not just to bring power to the shore, but also bring it inland. So really need to push power. We don't need it in the north of Norway. Nobody lives there. So we need to bring it to Europe. We need to bring it to Bavaria, where this BMW is made, which was mentioned earlier. So we will need a full upgrade of the system. And in my opinion, this upgrade is at least at the same level as the upgrades that were done in the 70s when we had to connect nuclear power and interconnect countries. We'll have a massive challenge ahead. And this is without onshore developments and solar developments, which are equally interesting. Next slide, please. So we're going to build this DC grid. It seems everyone agrees on that, and very nice that we have this consensus. DC is known. We have been advocating for this for over 10 years. EU is a leading DC technology provider. So yeah, this is the place to do. Oh, and it has been demonstrated in China. So why don't we have a DC grid in Europe? And this is a question not just you might ask, but also policymakers ask us. Next slide, please. Yes. So why don't we have, what are the technical hurdles? So To be honest, well, yes, HVDC is ready, but to have the suitable ratings to really make it appropriate for really long distance offshore, when we talk about some gigawatts, that means that we also need to have the voltage levels available, and that's not that long. Only the first systems at 500 kV are being installed. 640 is kind of ready. 800, that's not yet really there. So there's a really big power is still some developments necessary, but we're now in the ballpark where we want to be. It's kind of also not so super cheap, mainly the converter stations, which we inconveniently then have to put on a platform because you cannot really put them on the water, make them also very big and expensive investments. So that's also not really helping our development. They're large, complex, expensive. If we have such a system, control and protection is going to be more difficult. There are complex interactions between AC and DC systems. Interoperability is an issue, protection and breakers were missing. So basically, we said for 10 years that we're ready, but only now we are really at the point that we're truly ready, I would say. But there are also two other things that limit our technical development, I would say, is that, well, it doesn't really match well with what we're doing today. It doesn't really fit with the existing system, and we don't really have the experience to deal with that. And it's not helped that we don't have existing installations in Europe. I'll come back to the technical issues in a bit. So next slide. So, and this all accumulated to risk. Now, there are also some, let's say, regulatory and organizational risks, such as the legal framework is not designed to support any optimal grid investments or operations. It's very national-centric, very complex offshore rules, which doesn't really help to build something which is already a complex project. It is not clear who will invest, who will develop, who will operate the system. There are a lot of uncertainties in cost and benefits. Brexit is one of these it's clear that this is an uncertainty. If you're going to do an investment of a few billion, well, you would like to be sure that at the end you end up with a positive number in the bank. The standard, a further hindrance is that the standard investor, the transmission system operator, is by nature risk averse as a regulated entity and AC oriented. So it's not clear why they should go for a risky investment. This is not their normal thing of doing. And as mentioned before, you typically don't buy a grid, you buy in a line, and each line needs to be cost effective by itself. And each investment needs to be cost effective to all involved stakeholders. And it's not so clear how this reward is going to be. So, and admittedly, I mean, it's easy to say that things are not really working as they should, which is correct, but it's also not that simple in this European framework that we have multiple countries which have their own sovereignty to actually create such a level playing field for all the stakeholders and all technologies. Next slide, please. So how are we going to integrate this into the AC system? And I'm using one of the hybrids that Cornelis mentioned, where the hybrid AC-DC grid consists of a part AC and a part DC system. So yeah, we don't need to just bring it to shore. We need to have multi-gigawatt overhead lines. I don't know if you have any neighborhood committees in your country, but we have many of them that oppose any transmission line, and in particular overhead transmission line. If we're going to have multi-gigawatt transmission to Bavaria area, this will definitely be a problem. What is the right connection point? How far inland do we want to go? We cannot keep on connecting to the shoreline. Are we still going to have a reliability as we have today with 450 gigawatt of offshore wind? Are we expecting the same level of reliability? And what is N-1 in such a case? Is that no wind in, let's say, Scotland? Is that N-1 for Europe? Because that could be more than a 1 gigawatt outage. What are grid operations in normal operation and in a contingency? And how will you integrate the system in the different markets? And for that, I have this nice figure on the right-hand side, just to show if you have a 2,000 kilometer system in parallel DC and AC, and you have a 5 gigawatt of generation, let's say that's wind in the north and a load in the south of 5 gigawatt. The question is, how will you actually wield power over the different systems? Will you feed everything to the DC grid? Will you try to push everything as quickly as you can in the AC system, and then you Okay. Yes. And of course, depending on how you do it, different system operators will be influenced. If you look at the arrow coming from the north, you actually see, well, the right arrow, it will cross zone 2 in red, which basically is not influenced, and it will see a very major flow over its system. So that guy will not really be happy. So again, who will invest, who will own? TSOs, but also offshore developers and investors who will operate. Unlikely that the future offshore grid will be operated by TSOs who are because many of them will be involved, and it looks more like an RSC, Regional Coordination Center, that is going to be that coordinator or take that role. Next slide, please. So looking at what is going to happen, I will be very quick. Depending on, if you have such a big DC grid, faults will happen occasionally, and depending on how you protected the system, they will have a different impact on the connected AC system. Will you affect a single converter or multiple converters at the same time? This will depend on how many breakers you need to buy, how expensive your system is going to be. But on the other hand, it also will mean the expected amount of lost power will change as well. So you will need to think about your reserves that you have in your system. Next. And it will also determine the amount of a maximum loss of infeed that you can take. And maybe we can accept more for very short periods of time because a DC system is fundamentally different than an AC system. Next slide. We also need to think about how we manage our system. Here I have several small graphs showing how such a DC grid connected to 2 AC systems would work. You could imagine that AC grid 2 is, for instance, the Dogger Bank offshore wind farm, and AC grid 1 could be continental Europe or the UK or whatever, and the DC grid in between. And let's say one of the converters goes out in the top left. What happens is that all the other converters take over. That means that you have a frequency event in the AC grid and the voltage event in the DC grid. But also in the second AC grid, you see a frequency deviation. If you go to the next slide, on the left-hand side, you see the first thing that you need to do is you need to fix AC grid 2 because it's not involved. That means that you need to have some operational rules that create this unbalance to AC grid 1 alone. And in the next step, you need to do it per area, per control area. So that means that you have a different set of stages that you need to do. Next slide. And in the last step, what you need to do, you still need to fix the voltages and the frequencies in the system. So you need to completely rewrite your power frequency interactions. Next slide. I will be very quick given the time. Interaction or multi-vendor interoperability is a given. We absolutely need to have that, and currently it's a problem. We don't have that in large extent towards because we have black box models. We have an uncertain operation, and we also don't fully understand the AC system at the same time. Our models and our controls are not sufficiently known to be able to assess whether we're going to have safe operations, yes or no. The current day practice of using full replicas as a standard for testing all interactions cannot be maintained. In sake of time, I would say go to my last slide, because I think that's going to be yes. So I think that we will have DC grids in the future. We need them because otherwise we're not going to have our mass integration of renewables that we all want. The perceived risks and uncertainties have delayed current developments. We were ahead. Currently, I'm not so sure that we are. I have to say that the recent change with both TSOs and vendors make me hopeful that things could happen in the right direction. The required upgrade of the grid is fundamental. It's not a patchwork of solutions, and we cannot live with it. This is not how we do it today mentality. This has to go. We are going to change everything and deal with it. Regulation should never be the blocking issue. If regulation is blocking progress, then it's bad regulation. I think we need to be fair and say that as well. AC and DC systems interact. Fine, there is more control, but there are adverse interactions possible. That means that we need new tools, and the operation of the hybrid AC-DC grid shall be different from the existing grid. So there are changes. And the slides that I skipped are the following. Let's start to build the DC grid today. There is a significant societal benefit, even under different scenarios. It's profitable to do it today. Doing this demo would reduce risk, and given the high payback period, probably this should be a public investment. With that, I would like to finish. My apologies for too many slides, but feel free to give up.
Thank you very much, Dirk. And the audience will know now that when the panel go on holidays, they pack too many clothes. So it's a lesson for all of us, including me. So thank you very much. I think your concluding slide, Dirk, was on the money. That for me is a powerful slide. We got to do it. We've got the technology. In terms of questions and answers, I'm conscious that we've finished our allotted time. So I'm open to a few questions that we have. So I just asked the panelists to switch on their screens for a moment. We might get to a couple of questions and then we'll cut it short. I think the big question, I think a lot of the questions have been answered. There's been a number that have come in, and what we might do is follow up with the people who asked the questions. There was one question in particular that caught my eye, and it was in relation, and I think it's really one for Dirk, and it's in relation to as you get more and more DC grids, will the fault currents be too much for the AC grids? I'm not sure I got that question verbatim. It's in the Q&A. The short circuit on the system, the risk of protection malfunctions on the AC part, what can be done to help the AC system to deal with this?
Yeah, well, the DC converters are not really contributing that much to the short circuit, but there are a number of problems that could arise, typically with distance protection. Now, there are a number of solutions possible. One of them is no longer using distance protection or using different kinds of protection. Definitely more studies are necessary than the typical. It's no longer the typical installation that you have, but you could actually address, I mean, there are ways to get around that. So it's only at the moment that you get predominantly converters connected to a system, then we might come to another set of problems, but that's not for the next 15 years yet, and by then hopefully we'll have a solution.
Okay, thank you very much. So I think we'll wrap it up at that. There are a number of questions we didn't get to, but I think I don't want to run over because I know people have busy agendas and so on. I'd like to thank the contributors today and the panel. There's some more webinars coming in 2021 from Current, accelerating the energy transition. The next one is how dynamic line ratings can help optimize the grid, and that's on the 14th of January. And thereafterwards in February or March, we'll have one on cybersecurity, which is going to be very, very important as we move towards more solid state devices and controllable passive, move away from passive networks to more active networks. It's going to be crucial that we cover cybersecurity to keep the lights on. So thank you very much to all the presenters, and thank you for your commitment and slides. I wish we had more time, but we can only touch on it, and we may be back to you to help us answer some of these questions we have coming in, and we'll do that offline. So thank you very much to everybody, and thank you for joining us today, and have a great Christmas.
Thank you.
Thank you. Thank you very much.
Thanks, and bye, everybody.
Bye-bye.
Bye-bye.